So this is an old video, more than a year old actually, and it's basically a talk that I gave for my astronomy society. So this is mostly around slitless spectroscopy, and I hope that soon I'll get enough time to give you an update on my new advancements in slit spectroscopy. But nevertheless, I thought this talk was a really good summary of where I was at that point in time, and it does explain some basic concepts, as well as maybe give you some ideas. So just to keep it here and share it, I decided to upload that and download that and upload that here on this channel. So the agenda for today, I'll do a very brief introduction, including a little bit of a bio about myself, and then I'll dive into spectroscopy. How does it work? What is it? What is it really about? And then I'll explain my personal journey in how I have been using spectroscopy for my backyard here in Tombol. And I'll also share some of my discoveries, right? So the things that I observed using spectroscopy for my backyard. And after that, as I was saying, we can do the questions and answers. So yeah, this is me. My name is Matt Bourlagi. I was born in the Netherlands in Europe, and I moved to Houston about 12 years ago. Exactly 1 year ago, both my wife and I, we got started in astronomy, not knowing a single thing about anything in the universe to begin with. We came across a Twitter post from a woman that made a picture of a nebula using amateur equipment. And we were blown away because we thought that those types of pictures could only be made with space telescopes like the Hubble or the James Webb Telescope. So doing some research, we came across a YouTube video from Nebula Photos, Nico Carver. And there he kind of explains how you do that from your backyard with very modest equipment. So we got a 12-year-old Canon camera on eBay, secondhand, and we put it on a star tracker. And we started experimenting and making pictures from our backyard. And soon we realized we wanted to go to darker places so that we can catch a better light. And we stumbled across the Houston Astronomical Society, a club with more than 600 members, with its own dark side about an hour from Houston. And not only that, there's a huge crowd of enthusiasts, with everybody doing from visual all the way to photometry, and now also spectroscopy in this hobby. And it's been a very exciting journey. So my wife and I, Erica's my wife, we host the monthly meeting for astrophotography, the special interest group. And there's an interesting crowd coming together there of people talking about astrophotography. We also organized a couple of outreach events here at the local park called Clapwood. And last time we had more than 200 people showing up for a special eclipse themed outreach event. So we had the NASA ambassadors for the eclipse team talking about all the science and the physics around the eclipses, and really encouraging people to go and witness that yourself. So that was very exciting. My main interest today, yet as I'm exploring this whole new hobby for me, is astrophotography, and something that I call a backyard astro experiments. So I wouldn't call myself by any means a scientist, but what I'm trying to do is that by taking small experiments with my equipment from the universe, I'm trying to collect data and get a little bit more connected and interested in what's going on there outside of our atmosphere. And it's been a very rewarding journey so far. I started a YouTube channel. It only has 2 videos on it. But in that YouTube channel, I'm trying to capture a couple of those insights or best practices to help people get into spectroscopy. So that is where you can find me on YouTube. Here I'm sitting in my backyard during daytime with the equipment that I typically use during one of my imaging nights. So the best summary of my interest for stars is probably this picture of the Christmas tree nebula, pun intended, that I took also from my backyard. So this is a nebula that I shot also from my backyard here in Tombol. And you cannot find a single star in this picture. So in astrophotography, usually we take out the stars using artificial intelligence algorithms, and then we concentrate on amplifying the nebulosity, the nebula parts of the picture. And then sometimes we reduce the stars and put them back in, and some people actually prefer to never put the stars back into the image to begin with. So yeah, stars were usually just getting in the way of my nebula pictures, to be quite frank with you. But then under our real Christmas tree in December last year, Santa gave us this Star Analyzer 100 rating. And it is a small element that really started our journey in amateur spectroscopy at that point in time. We didn't know anything about this topic at all. So I'll hopefully share a little bit some of the insights collected over time. But mostly I want to share the excitement that spectroscopy can bring, in particular for us amateurs imaging from our backyard. I a little bit of a teaser, therefore, I put in this image. This is also shot with my own equipment. The universe is just full of secrets that you can unlock with spectroscopy. And it would be a shame if you're missing out. So spectroscopy provides a useful tool to really go after all kinds of information and elements in the universe, not just the stars, but also galaxies and nebula and so forth. So if you don't start with this, you're going to miss out. That's the best way to put it, kind of. So how does it work? What is spectroscopy? And I'm choosing a very pragmatic path here to give you a flavor. Probably a little bit pragmatic on some technical details, but I think it's kind of good to get a high-level overview to start with. So a little bit of history. Newton had a prism, so he basically put it in front of sunlight, and then he broke the light into different wavelengths, so he could turn the white light into colors. Right? Fraunhofer looked into the absorption lines of the solar spectrum, and he discovered that there was something going on there. Did an excellent job in documenting it and studying that through the end of his life. And he actually also firstly looked at those absorption lines in the star Sirius. Then another milestone achievement was from Cecilia Payne that connected astrophysics with spectroscopy. And I think today, if you look at our famous James Webb telescope, its main job is actually spectroscopy. So although we see really cool pictures on Instagram and Facebook from James Webb telescope, it's really out there to do spectroscopy. So spectroscopy is a very important element for astronomy, for real science and so forth, but it could also be that way for us amateurs. So how does this work? Well, we all know the album cover from Pink Floyd, Dark Side of the Moon. You have white light coming in and a rainbow is coming out. So basically in the visible light domain, so what we can see with our eyes, this rainbow has these wavelengths going all the way from ultraviolet, so that's very short wavelengths, about 400 nanometers. And then it goes all the way up to the infrared and above. So that's like 700 nanometers, so forth. So in between that, you have all the different colors of light. And if you look at the brightness of these different wavelengths, along those different wavelengths, you can make a chart out of that, so a curve out of that. And that is what people call a spectrum. So there you go. We went from a rainbow to a spectrum in 30 seconds. So there's some interesting cool things going on there. So if you have this continuous light source with this continuous smooth spectrum, and that light passes through a cloud of gas, then on the other side of that gas, when you look at that light, you will observe that there are some lines in that spectrum missing. And so basically you're seeing these absorption lines here. And it turns out that that pattern is very uniquely related to the properties of that cloud of gas, so to the chemical elements of that gas. Quite similarly, if that cloud of gas would be ionized, so it would generate light, then the light coming from that gas would also appear as in a very unique pattern. So you have these emission lines that follow exactly the same fingerprint as the light that you're missing in that absorption spectrum. So the properties of the gas are uniquely tied to those kind of small lines that you see in the emission spectrum or in the absorption spectrum. So this is basically the whole job for spectroscopy. So you have this kind of rainbow diffraction pattern of the light. Then you look at the brightness, and where you see these gaps, you can then study those gaps, and you can then correlate that to the chemical properties of whatever is behind that that's getting in the way of a continuous light source. There's basically the whole periodic table, right? Every chemical element has a unique fingerprint. And this is actually from a poster that you can order online. So every chemical element has a unique fingerprint. A couple to highlight is hydrogen, helium, oxygen. So you see that those are different chemical elements, different, and they have a very unique pattern. So they're quite distinct from each other. So for stars, there are a couple of really cool properties that you can use this for stars, right? So if you look at the temperature of stars, which is the same as this kind of weird ordering of the spectral classes of the stars, then there is a certain range where at a certain temperature area there's certain ionization where you can see the profile for these different chemical elements. So a very hot star, an O-type star, would have more of these features of these helium elements. And then hydrogen also has this kind of period here where around certain temperatures in this range, like an A and a B star, you see a lot of hydrogen lines. But when you look at very cold stars, 3000 and so forth, then basically you see more emission lines that are related to titanium oxide. So looking at the light missing basically from the spectrum, you can determine the temperature of stars. So this is another way to look at it. Basically, if you look at it same like stellar classes here, or the temperature is going from hot to very cold, then you're seeing here the fingerprint, for example, for H alpha, right? So that's hydrogen, H beta, and gamma. And this kind of peaks. This is more present around these A stars, but then it's gone for the stars for the G, K, and M category, right? So these are the colder stars. They are showing up with more of these emission lines around titanium oxide and so forth. So just by looking at the diffracted light from a star, you can tell the temperature, the surface temperature of that star. Another way to look at it, this is a little bit, it's a different way to look at that, is if you have a very hot star, so like an O-class star, then the brightness, there's a lot more brightness around the shorter wave length, so around the blue area of the spectrum, relative to the red side of the spectrum. Hot stars, they appear more blue. And then if you look at the colder stars, like the M-class stars, they have a little bit more red than the brightness in the blue area. So they appear visually also a little bit more red. So the colder the star, the more red it appears, and the hotter the star, the more bluish it will appear. So that's nice, but how do we make those rainbows? And in particular for the equipment that we have in our backyard. So we have a couple of really cool choices today. So I was just talking about the star analyzer grating that we got for Christmas. It's like a $200 investment into this grating. You can buy it from a store here in the US. And then for a long time, the next step into spectroscopy was a dedicated off-the-shelf slit spectroscope. And there's quite a big gap there because you're immediately looking into an investment of about $3,000 and more for that kit to get together. So unfortunately, I think a lot of people kind of gave up after their first experience with star gratings because it was such a big gap. There's a new contender though that came out very recently, and it's called the Star X Do-It-Yourself Kit. And this is a variation on a solar observing project called SOLAX that was originally developed in France. And it contains 3D printed parts that are publicly available. So you can have it printed by a shop or your public library, or you can print it yourself. And then you buy some optical parts. And once you've assembled all that together, you have probably spent around $1,000 or so. But the resolution is absolutely close to what you can call professional level or semi-professional level requirements. So it is absolutely punching above its weight class there. So now we have those different options for our hobby, and I think there's a much easier path to grow into spectroscopy as earlier. Today, though, I'm going to talk mostly around the star analyzer grating that we got for Christmas. So how does that work, right? So basically, this kind of filter here, it's like a filter almost, right? It's a piece of glass, has small grooves on it, like tiny, tiny grooves. And when a straight, like white light hits those grooves, then uh, at each gap in those grooves, it basically acts like a point source for light. So it works like you're throwing two stones into a pond, right? You get waves, and these waves, they're interfering. And sometimes you get constructive interference, and sometimes you get destructive interference. And that's basically the same what's happening here to the light, right? So some of the light passes through as a what they call a zero order, and then there are all these different kind of rainbows diffracted from the light for a first order, a second order, and in the other direction, a negative first order and a negative a second order. So, so this is basically the same almost as a prism, but it is much more compact to build into our amateur equipment. So here we have our same grating again. So a little bit deeper dive on that. You have the starlight coming in, then you have this diffraction, and then you see the zero order. So that's the original star. And then you see these first order and second order diffraction patterns. So what I call the rainbows from the stars. These gratings, they are quite worth their money because they are blazed. So different from diffraction gratings that you can get via some Chinese warehouse. These particular gratings are blazed, and that means that they have more light that they throw into the direction of the first and the second order than that they throw into the negative first and second order. Another thing is that the size of this rainbow and the stars is basically determined by the geometry, right? So the distance from the grating to your camera that you're using to capture that image. There's a little bit of optimization that you can do there to increase that distance and then make sure that you get a large enough rainbow, basically, that you can capture that well with the pixels of your camera. This process overall, though, is distributing your photons, right? So the photons that go in, they now go to different orders of rainbows. So you're losing some light. And basically, the first order rainbow here is about 5 magnitudes lower than the star that originally came in. So if you have equipment that has a limited magnitude, right? So you can observe stars of magnitude 12, for example. If you then add this grating to it, you're basically losing some light, and you can only image stars that are magnitude 7. So you're sacrificing a little bit there, but it's still not too bad. So basically what we do is then put our CMOS sensor there, our camera, right there, and then we make a picture of the zero order star and then the first order diffraction grating. I also always take a little bit of a wider picture, so I can also subtract the background from the actual diffraction pattern as well. So I can further then improve the signal to noise ratio. So that's how it works in a very basic principle. Now this grating, you can use that in different ways. And one way is what they call the objective grating setup. And this is where you put this grating in front of your camera or in front of your telescope. So you can buy like a small adapter ring that matches your camera lens, or you can 3D print a holder. You can even use some carton or duct tape, but you basically put it in front of your whole optical system. The alternative is using this grating on a T-nozzle, and then basically you screw that onto your camera, and then this goes into your telescope. So the advantage of that is that you have the full light gathering capability from your telescope, which could be a very high aperture telescope. The disadvantage is that you put this grating into a converging beam, right? So the light that goes onto the grating is not exactly parallel, and that causes some issues. And I'll show you in a little bit how bad that can get. So you don't have that light gathering capability at all with this objective grating setup, because now your aperture is really constrained to this tiny small window of this grating that I screwed onto my camera. But it is such an easy way to get started. So that's where we also got started ourselves. Let's see. So this is kind of the start of our journey. So it started with our Christmas tree, and then our first step was to make this objective rating setup. This is what it looked like. So I have my Star Watcher Adventure tracker. It's just compensating for the Earth rotation. It's making things very convenient. And then I connect this 12-year-old second or third hand camera to a laptop that runs SharpCap. So with SharpCap, I can just take pictures very conveniently. And that's basically all. So our first night out was around Christmas time. And what better target than your neighbor's barn, right? So here you see the Christmas lights on our neighbor's barn. And you also see the light that's usually there. That's a sodium vapor light. So the Christmas lights, they are Edison lights. So they are traditional light bulbs, really warm light. And you see that the spectrum is really continuous, right? So it has all these, in the visual domain, all these wavelengths is relatively bright. You see all the different colors from blue all the way to red. The sodium vapor light is kind of interesting though, right? So here you see our 0th order, like it is a star, and then you see the spectrum, and the spectrum is very, very intense around yellow, and also very intense around cyan. But then in the middle, there are some very obvious gaps. So when you Google spectrum sodium vapor light, then you will see exactly the same as we just documented and experimented with our first shot using our spectroscope. So high brightness around those yellow areas, almost nothing at the green, and a little bit of that peak around cyan. So our very first picture was actually a very interesting spectroscopy project. Then as we were out there, you swing your camera around to the night sky. So my wife said, like, why don't you just put it up and see what happens? And that's what we did. So this is our very, very first picture of a random place in the universe from our backyard using this same setup that I was just showing. And then basically every bright star turned into a science project. Our mind was blown away. So already with this first picture, you see like a red star here at the bottom, and you see some really interesting things going on there. You see other stars that have light missing, like absorption lines. You see some more fainter stars over there. If I would take more pictures and I would stack them together, I'll improve my signal to noise ratio, I can probably catch them as well. Everything in the night sky now turned from a black and white dot into a rainbow, and it was just super exciting. So we this is where we got hooked. So our next object of study was Orion M42, right? So a very bright emission nebula. And most people that do visual astronomy can see this nebula very, very well because it's so bright. So here you see the original nebula, the 0th order. And then the first order is that spectrum. And you see a very high peak coming up here with H alpha and O2 probably here in this cyan area. So you see basically exactly what we would expect, that ionized cloud of gas to be. It now creates light. And now you have those emission lines that are coming from an ionized piece of hydrogen and helium. So that's pretty awesome. And then just a more regular star, right? That is here in B. So the 0th order is here, and then you see the spectrum going from blue to red, as you would expect. What is kind of funny though is that this spectrum is in the other direction, right? So this goes from red to blue. And this actually turns out to be the negative first order spectrum of the star that is over here. So it is a lot fainter than the star above. Now, of course, they could have had different magnitudes. But the way that these gratings work is that they are blazed. So they are a little bit brighter on the positive orders than the negative orders. Didn't stop here. So the next step was the Pleiades, right? A much more crowded star cluster with lots of things to observe. So this is 120-second exposures using the same kit. And then we just stack the images using serials. That's a typical trick that you do in astrophotography. You combine all these small exposures, and it's almost looking like a very long single-shot integrated picture. But you really see that there's a ton of light and lots of objects to study just from one corner of the universe.
And you also see the first kind of drawback of using this grating. This is what they call a slitless spectroscope. So you don't isolate with a slit one particular star. It takes a broad picture of the whole field of view. So the spectra, they're sometimes getting photobombed by the stars that are in the background. So they interfere with the objects that we try to catch. And for a long while, I thought that was also going on here in this place, where I have this kind of red dot sitting on top of this spectrum. And so I was putting together this PowerPoint. I was like, no, there's actually something really going on here with this very particular star. And I will give you another example in a minute. So this is an emission from a star rather than an absorption line. Pretty cool. I'll get back to that. So we got plenty of rainbows, right? So we got so many rainbows. There's so much stories there in the universe that you can grab. But you really get into it when you're able to translate that rainbow into that brightness wavelength graph, the spectra. And at that point, you're down a rabbit hole in spectroscopy. There's no way back. You're going to get completely submerged into the topic. And it's addictive. Just a small warning. Luckily, there are great tools available today to do that. So you don't have to do a lot of math yourself. You can do, but you don't have to. And what we kind of settled on was BAS Project. So BAS Project is a free tool. It's developed by somebody in England. There's a really active community around it online as well. Very easy to use, very robust, and it's free. So everybody can give it a shot. A next good alternative I would recommend is RSpec. It's a one-time fee of $100. It's even better documented. A lot of YouTube videos about that by the developer itself. It's developed by Tom Field, and Tom Field is an absolute evangelist for amateur spectroscopy. So he is offered kind support always when you're getting stuck there. So that's a great other option. And then you have some more advanced software products or packages. They're all free that are available and popular in France, like ISIS and SpecInt. If you want to use Python, that's also possible. There are plenty of libraries specifically for amateur spectroscopy as well. So, of course, then you're getting a lot deeper into this whole processing stuff. So, from a rainbow to a spectrum, right? How do we get there? There are basically two things that gotta get figured out. One is that you have an image of basically that diffraction rainbow. And that image has certain dimensions and it has pixels, right? So you're looking at the brightness of these colors along different pixels. So one of the challenges is how do you convert that to the corresponding wavelengths? And that is what you fix with this step called calibration, step one. And then there's a second step that you could take, and in many cases makes a ton of sense. And that is where you are correcting for all kinds of losses in your whole instrumentation, but also as an effect of the atmosphere. And that is what I call step two. That is the response correction. I made a YouTube video on this and how you use those free software tools to walk through that you can find on my YouTube channel. I just want to give you like a high-level flavor of how this clicks together in today's presentation. So step one. So basically we have now loaded up that 0th order, so the star, and then its diffraction pattern in BAS Project. So you can basically open up a picture, and then in BAS Project you can cut out this small letterbox envelope surrounding your star and that first diffraction, your rainbow. In this case, I used a monochrome image, a black and white image, because this was shot with a monochrome camera. If you have a color camera, then you can first translate your image to grayscale, and then you can do the same thing. So what we need to do is to basically understand the brightness along those pixels or wavelengths eventually. And the way that this works is that they basically take the column sum, so the sum of the values of the pixels, for each column at a time, and that is what you see in the graph here below. So the star here is very bright; it's almost saturated, right? So that is what you see here as the zero order brightness of the star. And then when you look at the diffraction pattern, the spectrum, then you see that this particular star is missing some light at some particular places and some particular pixels. Now, and I'm taking advantage of that when I'm calibrating, mapping basically pixels to wavelengths. I'm taking advantage of these unique features of this star. So I know that this particular star, and there are plenty of those, is a type A star. So as I showed earlier, it has very strong hydrogen absorption lines, and they happen always at the same frequency. So this software package is super convenient because you basically click on those features and you say, well, this is a hydrogen absorption line, and it then automatically scales the x-axis from pixels to wavelengths. So now I know, and I basically completed my step one, what the brightness is per wavelength. So, so normally you would then go to step two, and I'm going to go in that in a minute. But you don't always have to do that. If you're just interested into very local analysis, you don't always need to do the step two. So I think a good example is the star that I was walking into with the Pleiades, and there's like a similar one in Cassiopeia. So this was a star, and I also thought that I was photobombed with another star overlapping with my spectrum. But when I loaded this up in Bass Pro and I did that first step to basically go from pixels to wavelengths, I could show that this small light blip here is at a very unique and particular frequency. So I compared this with the spectrum from the library that's also in those tools. That is the same temperature class, right? So it is a B-type star. And usually for that star, you would expect that you have absorption lines at those wavelengths. But what I have is that I have these emission lines. So there's something very uniquely going on here. And I basically, without knowing anything about this at all, I rediscovered myself that this was a BE star. So the B stands for the temperature class, so that's a B-type star. And the E stands for the emissions of these types of stars. And what happens is that this star is spinning very, very fast. And it has this ionized degradation disk, like a disk of hydrogen. And because that's ionized, it's then causing those emission lines at exactly the pattern where you would expect emission lines to happen from hydrogen. So this is a very peculiar object in the night sky that you're able to just discover from your backyard, basically. Now, there's a lot more to it. These emissions, they actually change over time. So if I would do this experiment every month or so, if I would return to this star every month, then I could probably observe some changes there, and I could study that and log that and get really into what's really happening with this particular star. So even though you only did that step one in that kind of process that I was just explaining, you can already do pretty cool stuff. Now let's get into the nitty-gritty when we go to step two, right? So the response correction. First of all, what are we trying to achieve here, right? Basically, we have our target star, right? So we have a star outside of the atmosphere. Then that light goes through the atmosphere, and it goes through our telescope, through our grating, through our CMOS camera, before we actually observe the light at those different wavelengths in the spectrum. And this whole chain of events and equipment has its losses, right? And these losses, they are also dependent on the wavelength. So first of all, our CMOS sensor has a certain quantum efficiency, a sensitivity that is not the same for all the wavelengths. So if you buy a camera, an astro camera, you're very familiar with this because you're paying top dollar to get a high sensitive camera. And you probably would study these plots when you have to decide between the different astro camera. The grating itself, though, also has a certain wavelength dependent efficiency. And then this is all equipment related. So this would stay rather the same night over night. But what is a little bit more different is the atmosphere. Right, the atmosphere itself has dust, water, particles, ozone, and also the sky mass itself, the thickness of the atmosphere as we poke through the atmosphere. If I take an image of a star that is straight above me at zenith, then the atmosphere that I go through is very thin. But if I take an image of a star that's more closer to the horizon, then that layer is very thick. So depending on where I'm trying to catch the spectrum from a star, and depending on the weather conditions, I could have a very different atmospheric loss. So what I observed with my camera, what comes out of my camera, that shape, that continuum, is not exactly similar to the shape that you would expect from your star. So let's call that what I observe, right, for observing. So the trick that amateur, So basically our objective is then basically to understand all these losses, right? And then correct for those losses so that I can get a continuum that's closely related to the star that I'm trying to chase. So there we go, right? So the trick that amateur spectroscopists use is that there are a couple of very well documented and researched stars, and they are in a library, and you have spectra that are in that library. And all those software tools that I just talked about, they have a database of those libraries in that software program itself. So you don't have to download that from the internet or do any math yourself. But basically what scientists did is that they looked into a couple of different types of stars, did extensive modeling on that, and they said, okay, this star should actually look like this. So you have a standard star from a library. And what you do is that on a night out with spectroscopy, you're trying to find some stars that are close to the object that you're trying to study. And those stars that are close, they need to match the stars from this library. So in that same piece of the atmosphere of the sky, I can create a very accurate model of everything that I'm losing between the actual star and my observation. So what I do in the end is that I just divide my observation by the spectrum of the standard star, and then I have a model of my response. And that model now contains all my atmospheric losses and all the losses in my equipment together. And it will change night over night, and it will change depending on the location or the point in the sky where I'm studying. So with that model, though, I can then correct my observation. And then basically I end up with this kind of purple line here. And this purple line is much closer to what the scientists say that standard star should look like. And I can use that same model then on the target that I'm trying to pursue that evening, because it basically corrects for all the losses in the atmosphere and the telescope and so forth. So this is our first kind of step going from a rainbow to a spectrum. So here you see this blue line that basically came out of my Canon camera, pretty different from what a star continuum should look like, although the local features are kind of the same, right? These absorption lines they look kind of the same. This overall trend is very different from what a star spectrum looks like. So using that reference star, like the green line, I can then correct for that, and then I end up with this purple line. So this purple line is now closer. It's not perfect, but it's much closer to the actual broad shape of what a type A star should be. Now, this is very rough, and this is our absolutely first one, so it has some personal historic value, I think. Later on, I will show you what a really good calibration looks like, I promise. But this is where we were with that objective grating setup. So just screwing that filter in front of your DSLR and just exploring the universe, basically. We wanted to go further because that tiny little hole in front of our camera was basically stopping down, reducing a lot of light that I could gather with this objective grating setup. So we wanted to go faint. We wanted to go for faint objects in the night sky. And the way that you do that is to move as a first step to this converging beam approach. Then I can go from something that you have f10, so very, very not light sensitive, to something that's closer to my actual telescope. So then my telescope is f4.9. It's a Red Cat 51. So here you have my setup, where I basically move that grating now between the telescope and my camera. So you can use a couple of adapters to get that done. And from the outside, this actually looks like a pretty standard today astrophotography rig. a wide field telescope. It's an apochromatic Redcat 51. So the focal length is 250 millimeters, very wide. It's guided. It is on a harmonic drive AM5 unit. And then you have a camera in the back. In this case, this is a mono camera. So this is now basically a setup where I can go after much fainter objects than what I could do before. A big disappointment though, because suddenly all my resolution was gone. So the only thing that I could shoot were these like really soft blobs of spectra. And I just could not figure out what was going on. And I spent weeks and weeks and weeks doing research and tweaking into figuring out what killed my resolution. This is a huge topic, and I don't have time to put it right now into this talk, but I made a YouTube video about it. So that's my second YouTube video, where I go in depth on what is killing resolution for certain types of setups for amateur spectroscopy. And the good news is that there is a solution to it. You can add a small prism in your setup, and that fixes some optical aberrations that exist for certain types of wide field, very fast telescope equipments. But I claim that without this prism, it's going to be very hard to have high resolution and a good light gathering capability with an astrophotography rig that I have. So after I applied that fix, though, I got a phenomenal high resolution, like resolution 300, which is pretty good for a setup like that. And here you see an example of a K-class star. So that's a much colder star, so it has a lot more going on there. And you could spend evenings and evenings on exactly labeling and figuring out what absorption and emission line is in here. But the main point here is that there's a lot more detail in this picture than what I've been able to do before. So now I have a setup that is able to go after very faint objects and at the same time crank out a relatively good resolution. So a much better picture, and now calibrated as promised, is of series is this one now. So this is also for my rig, but now fixed with that prism. And this is what a well-calibrated picture looks like. So very sharp absorption lines around hydrogen. And you can even see some telluric bands. So this is from the Earth's atmosphere, oxygen and water and so forth. So a lot more detail in that spectrum that I was able to obtain. So yeah, going after faint objects, this one was high on my list. So this was a Wolf-Rayet star in Canis Major. And this is a really odd and peculiar object. And what you see here is a spectrum that I took with 1-minute exposure. So literally 10 minutes of exposure time. And there's just so much cool stuff going on. And with astrophotography, you basically, the star is in the middle of the Dolphin Nebula. That's quite famous. But just being able to catch this spectrum and then look at all these features was a super exciting thing. So Wolf-Rayet star, they're at least 25 times higher mass than our sun. And those are stars that are literally coming apart. And what happened to this particular star is that the hydrogen layers have flung off. And you're looking at the hot helium-rich core. There are huge interstellar winds, more than 2,000 kilometers a second. And they ionize that helium. And you get these very broad emission lines that you see here in purple. And on top of that, certain specific elements are also ionized and exposed. So you see some carbon here and some nitrogen. And depending on what types of elements are in these Wolf-Rayet stars, you can then infer at which states of the evolution, of the destruction, this Wolf-Rayet star is at. There are about 200 or so Wolf-Rayet stars that are known today. And actually, this is a great season because there are a couple of those also in the Cygnus constellation. But just being able to like shoot a spectrum and then dive into the nitty-gritty of what you're seeing here has been a phenomenal experience. Last thing I wanted to show is a planet. So Uranus, one of our ice giants. And basically, when we look at Uranus, we see the reflected light of the sun. And our sun is a G-class star. So the light from the sun goes through the atmosphere, some of the light is absorbed by Uranus, some of it is absorbed by some features in the atmosphere, and then some of the light is bouncing back to my telescope here in Texas. So what I wanted to explore is if I could pick up the methane gases in the atmosphere of Uranus. And aside from the calibration star that I talked about to calculate the wavelength and so forth, you have to figure out, like, okay, what is the portion that is coming from the sun, and what is the portion of the light that basically comes back as a reflection to my telescope. And because it's in the middle of the night, you don't have access to the sun. So what you do instead is that you pick another G-class star like Capella. And then you can basically derive the atmosphere spectrum by dividing the reflection from Uranus with the spectrum of the G-class star. So that's what you see here in this picture. So in green, you see the spectrum of Capella. So it has some dips here. It's not a lot of light coming from a G-class star at these particular wavelengths. And then a little bit further away, there's not a lot of light being produced in the spectrum there as well. And then in blue, you see the actual reflection light from Uranus. So that is then the resultant of the light that is getting lost in the atmosphere and the light that never went in because it was never emitted from the sun. So if you look at this particular dip here, for example, you see that there's not a lot of light from Capella going into Uranus. So there's not a lot of light that comes back from Uranus. And then these higher wavelengths here, kind of the same thing. There's not a lot of light coming in, so there's not a lot of light coming back. So that so what I just showed you, that small calculation, is basically then the difference. So that black line is showing exactly the light that is absorbed by Uranus. And quite interestingly, you see these huge absorption areas here. And when you do look that up on the internet and so forth, they correspond exactly to methane. So basically, with my exposure, like a 15-minute or so experiments from my backyard, I can show that there's methane in the atmosphere of Uranus. So that was very excited, and here in the house we were excited about this for weeks after we found this. So that's kind of where we are right now. And my next step is to build this do-it-yourself spectro kit. I got the parts in already. I have to assemble it and find some more optical parts. And this would definitely take my hobby to a next level of detail that I can see and new objects that I can pursue. So I hope I was able to share a little bit the excitement that this caused and the new doors that were basically open for me into this hobby. So a little bit of a summarized sales pitch then to you, like, hey, I invite you to expand your universe. There's just so much more to see and experience. And there are a couple of true advantages where I think spectroscopy really stands out for amateurs. One is that it's completely tolerant to light pollution and the full moon. So you don't have to wait for just those couple of days around the new moon to go imaging. You can literally do this from your backyard. Some people do that right next to the Eiffel Tower. So the other thing is that all your equipment that you already have in astrophotography and your skills, you can leverage that. There's not a lot more that it takes to make a picture of the night sky. And then the costs are relatively small. So that star grating that I was showing is literally $200. And on the mathematical side, it's not very complicated. Most of that is already automated in these tools. So it's not that complicated. And for me personally, what I found most exciting is that this is truly galaxy season proof. When there are those months in the year that I cannot see the Milky Way, then most of my nebula photography targets are gone. And then I just have to wait for the Milky Way to come back. But with spectroscopy, there are hundreds of targets every day that you can pursue. So this really, for me, opened up a really interesting chapter in the hobby. There's something uniquely, though, why today is a good time to do this. So if I haven't told you yet, then listen to the following. Last year, there was a major breakthrough in astrophotography. So we got harmonic drive mounts, and that completely solved all the tracking burden on astrophotography that people had in the past. And in addition to that, You had tools coming out like the ASI Air, and Nina came up with a new update. So making great pictures of the night sky is much easier today than what it was 2 years ago. You have access to stacking software. So as I was showing you earlier, you can combine multiple exposures and get to really, really faint objects. And there are all these new projects, 3D printed projects out there that you can pick up. And you can build your own astro equipment, your own spectrographs at very low cost. And as I showed a little bit in a YouTube video that I referred to, wide field astrophotography systems have a special sweet spot for amateur spectroscopy. We have tiny sizes of the star, and then when we solve that issue with the aberrations that I was talking about earlier, you can basically get a very high resolution setup that's portable, and it's very similar to your astrophotography setup that some people already have. The AAVSO, the American Association for Variable Star Observers, has picked up on this. And they have started a whole new series for beginners, amateur beginners in spectroscopy. So they also are hosting meetings, having YouTube videos, quite recently a lot more on this particular topic. So there's never been a better time, and it's a great opportunity for you to expand your universe. So some resources, right? I was mentioning our special interest group every fourth Wednesday of the month. I was mentioning Field Tester System, that's the supplier of these gratings and the supplier of RSpec software. And I also just was talking about the AAVSO, so that's a cool organization. Even though maybe you're not very interested in pro-amateur science, I think they still have a fantastic platform, including mentors, to help you out getting started with spectroscopy. Then I read a couple of books. They are absolutely amazing and really relevant for this topic. My favorite book by far is the book from Robert Buchheim. This is backyard astrophysics exercises worked out that anybody can pick up. And there are a couple of really strong chapters there on spectroscopy as well. So it's much broader than spectroscopy, but it is one of the best books that I've seen so far in the hobby. If you're interested in grating spectroscopy, Ken Harrison makes a great book there. Slit spectroscopy from the French community is now also available in English. And then you have some more bigger books that really go into the depths of physics from Tripstein and Walker. And in particular, the Spectral Atlas is a really nice reference to have so that you can decipher all the emission lines that come up. So that in a nutshell is my experience so far since Christmas with backyard spectroscopy. So we have time for questions and answers, hopefully. So let me just go to the chat.